That's starting to buffer there. Oh my goodness. All right, where's me? There's me. All right. So we talked about this a little bit. Let's talk about the superposition principle. No matter how horrible that quiz was, you got to get over it and realize I'm going to use that quiz as a learning experience for you guys too. All right. Let's talk about electric fields and focus on something and move forwards. All right. So E total is equal to E1 plus E2 plus dot, 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 dot. We know about force vectors, right? You add up force vectors to get the net force on something. You could add up electric field vectors to get the net electric field on something, all right? And so now what I'd like to look at, make sure, let's go to right here. I'm at page 19 in my workbook. And remember, I sent you guys the PDF of the workbook for the first 3 chapters. A couple of things I'll mention. It looks like, I don't know if it's the post office issues right now, but everybody's having trouble with shipping delays and all kinds of stuff. The bookstore evidently refused to order my books without telling me. I don't know what's going on, so I'm trying to figure this out. So we'll just keep doing this. But if you have not already ordered the PDF workbook from Amazon, I would get on that right away. Note, if you tried to order it and it says unavailable, just go back in in a little while. And it turns out it's print on demand. So I think there's something weird that happens when too many people order all at the same time. It will get backed up. So, but it is available, and all they do is they just print another copy and send it to you. And I did that because it's cheaper than the bookstore by several dollars. So I'm trying to save you money, not give it to Jeff Bezos, but he ends up getting a cut because of this system. And also the bookstore is notoriously bad. That's why I had to do something, because they're just, no matter what I do, they're screwing it up. So apologies. I'm working on getting that in the bookstore too, but they're just dragging their feet. Okay, sorry. All right, so we're on page 19. I'm all over the place. We have an electric field. Now think about this. If you take the electric field, you could have the electric field of 1 point charge and the electric field caused by a 2nd point charge, and you could just have a couple of charges here. Maybe there's 1 and 2, maybe even a 3rd one, okay? And so at some random point in space, let's say this is number 3, you know how this works. You'd say, I'll get the electric field from this one. That would be away. That's E1. The electric field from this one, that's E3. Maybe they have the same charge, maybe different, I don't know. And then this one, it's a negative charge, so it would pull it in. Imagine, again, remember, if I put a plus charge here, it would be repelled by that. That's the direction of E1. If I put a plus charge here, it would be repelled by that. If I put a plus charge here, it would be attracted by this one. And so we know that the total electric field at this point is the sum of these. Okay, big deal. So now what if you have an object like this? Let me try and do this the same way. Let's say we have a rod here. And because we just did lab, you know you could rub this with fur and get a charge on there, right? Now the issue is, if you take a plastic rod and rub it with fur, the charge could spread out over the whole thing. Or maybe this is a glass rod. I think glass was positive. So again, I'm not drawing all the charges. I'm only drawing the excess charges. Imagine if you had all those excess charges distributed, okay? And whoops, let me get these guys in here. Okay, all right. Sorry, it's just, okay, there's a lot going on here. All right, so now imagine, instead of thinking of this as a rod, think of it as just a large number of point charges, right? So we have a bunch of plus charges here. And now let's say I pick some random spot in space. How about right here? I know that if this was a plus charge, the first charge would push that way. The next one would push a little this way and it'd be smaller. And then you could start adding up all these charges. Right? You could add up all these little arrows and get the net field here. Well, what you could do is instead of calling them E1, E2, E3, you could call this DE for a small infinitesimal amount of charge. And then what you could do is instead of saying E total equals the sum of E sub I from I equals 1 to n vector, you could then just change it to an integral, right? Because that's what an integral is. It's just a different way of doing a sum, right? So you could say it's the sum of all the little DEs. Oh my gosh. Okay. So the idea is all we're going to do is we're going to figure out how to write DE and then how to do the integral. The integral part's pretty easy once you figure out how do I write this DE. And again, for those of you, I might have been a little bit slow admitting you because I've got so much going on here. It is page 19 in the workbook that I'm looking at. And again, you've got the PDF or it's in Canvas, okay? So instead of just adding up point charges, we're going to figure out how to do this with an integral. That's it, right? And in lab next week, this is going to be the integral that you do, right? You're going to do a numerical integral in Python and just say, oh, what's the charge on one and add them up. All right. So it's funny. There's just like bells and stuff going off all the time in my head right now. It's crazy. People coming in and out and I don't know, whatever. So here is the procedure for you. And maybe I'll put it up. Let me share the screen here. Oh, and let me get the chat. Okay, got the live stream. Yes, okay, good. Thank you for the reminders, everybody. Okay, so that was all that old YouTube. Okay, so let me do this. Yeah. I think I'm going to do that. I'm going to make somebody a co-host in case people come in and out. Just give me a second here. Okay. There we go. That way, if people are coming in and out, somebody can handle that. All right, so that's good. Now let me share the screen real quick. Whoops, not that one. Not that one. This one. Here we go. All right. Oh, that's too far. It's not quite. Man, this is a lot easier in person. Come on, almost there. I think it's one more. Sheesh. Sorry I'm so slow today, people. There it is. Okay. Okay. All right. So here's the general strategy for this. Okay. So, and this is for the rod shape. You're going to see that each different shape is going to have a slightly different strategy. So I'm going to try and draw this out and tell you which step I'm working on here in just a second. Okay. So hopefully you've got that. If not, maybe take a screenshot of this, or again, this is on page 19. It would really help if you have that open somewhere in front of you, but I understand the issues we have. Okay. So I'm going to take a rod here, draw it, and then try and go through this stuff. Okay. And now I'll just pick some random spot. How about over here? And maybe this is what my coordinate system. I'm just making up a problem to do this. Okay. So I'm going to pick an arbitrary chunk. Okay. So here's my rod, and we'll assume it's, again, positively charged. For now, we'll just assume it's uniformly charged. I'm going to pick a random chunk of this thing right there. Try not to pick exactly halfway. Students get in a bad habit of thinking, oh, everything's L over 2 or something, all right? So I picked a random chunk. The next step is write down the R vector from the source, which is this little piece here. This is a tiny amount of the total charge. Okay, so this is a tiny amount of the total charge on the rod. It is dq. This down here is the point I care about. Okay, so remember, I want to go from the source of the electric field to the point of interest. I want to go from the point charge to the place I care about. Okay, this is my point of interest. Oftentimes we usually just call this the point P. Okay, so I have some point P here. There we go. This is my R vector for that particular DQ. All right. And now I need to figure out R and R hat or things like that. So let's just say in this particular case, a good name for that distance is probably X. And perhaps this distance here, we could just say is A. And again, I'm making up a problem on the fly just to kind of show you how these steps go. Okay. So in this case, R vector is, let's see, negative X in the I hat, because we're going from the source down to here. Okay. We're going this way from the source to the POI. Okay. So negative X in the I hat, negative A in the J hat in this weird case. Now right away, I can get R, which is just going to be X squared plus A squared to the 1/2, or you could write square root, but in general, this ends up being a better way to do it. You'll see why. Okay, so that was step 2. Now, oh, that was step 3. Oh, and I guess if you want it, here's R hat. So that would be R hat. Okay, so that was finishing step 3. Now I could do it with the R vector over R cubed, or I could do it with R hat over R squared, either one, and I should get the same results. Okay, so that stuff's all there. Hopefully you've got that. I'm running out of room, so I need to read the next thing. Figure out lambda. Okay, usually this rod has some length. Let's say it has some length L. That's supposed to be an L. All right. Now, if I have charge Q, and I'll call that capital Q just to distinguish it from this little q, you could probably guess charge per unit length, which is what lambda means, is going to be Q over L. So in this case, if you have a uniform rod, the charge density is charge per unit length. Again, we're not talking about charge per unit volume. We're talking about charge per unit length because we have a rod, which you could think of as a one-dimensional object, right? For the most part, if I want to tell you a place on this marker, I could just tell you how many inches over, and you'll be like, yeah, I got the idea. If I say 3 inches, 1, 2, 3, right there, you'd say, okay, I kind of know where he's at. Now, if I zoom in close enough and look at it, then it starts to look 3D, right? And then you might want to talk about X and Y coordinates or something. But in general, when it's really far away from the screen, just telling you the X coordinate pretty much tells you exactly where you're at. That's the concept here. So this has units of coulombs per meter. All right, so this density is in coulombs per meter. It's not a mass density, it's a linear charge density. Coulombs per meter, linear. Okay, I'm going to pause for a second on that. There's a chat there. Yeah, there you go, Alexis. Totally true. Now, fortunately, Alexis, I know we're not going to finish this problem, right? This is a particularly juicy one. All right, so good to know. All right, so there's step 4. Now, now look at this. How could I get this charge and relate it to X? This is the trick that you've got to do with these problems. So we want to do an integral. We're used to doing integrals over the length of this rod, over X. So what I want to do is use the density to rewrite the charge. This dq is a tiny bit of length, dx, times the amount of coulombs per unit length. Think about the units. This is how many meters long that is, like maybe 1 micron long. And so I take however long this is times lambda, and I'll get a charge. So right there is how I convert dq, or a small amount of charge, into a small amount of length. Okay? All right. So let's see. Hopefully that's all right. Nothing in the chat. Okay, cool. All right, so now we're up to step 5. And I'm just going to show you where we're at right now. You've got that screen. Let me just make sure you got all this because I know everybody's kind of in different spots with this. So what we did is we did this, we did that, we did this, and now we're right here. So we kind of did the first 4 steps. We're ready to do the guts of this. So this is what we want to do, okay? What we want to do is we want to say, get the total electric field by adding up each one. And so the idea is we've written these parts here. Whoops, sorry, let me go to the one below. This one right here. We have figured out dq. We have figured out r in terms of the variable x. So if you go to a different x, you're going to get a different value for r, and you'll get a different contribution to the total electric field. Now I'm running out of room here. So what I'm going to do is this. Hopefully you can remember this. I know what they are, I hope. And so now in this case, I know the total electric field is going to equal dE. Add up all the little electric fields, which in this case is going to be K dq r vector all over r cubed. Or again, you could do r hat over r squared, okay? In this particular case, all right, we're going to do K. This is dq was lambda dx. All right, and then let's see, the r vector was, I think it was negative x in the I hat, minus a in the j hat. And then all of this was over, notice we have this cubed. So a cube of the 1/2 gives us something like x squared plus a squared to the 1/2, and then we have to cube it, which is 3. So now at this point, you'd be saying, man, I do not want to do this integral. Fortunately, this one happens so much. You can see I put an integral table there on the back of the book that you'll never get from Amazon these days. Jeez, what a brutal semester already. Anyways, but there's going to be some tricks for doing some of these integrals. I put the most common integrals back there for you. So that's something that you would have right at your fingertips. Also, a lot of times, well, I know what I did for some of these questions was I asked you to set up the integral in the quiz and not do it. And then just write down the answer or select the answer from a multiple choice, a list of like 12 different possible integral setups. So then you could say like, oh, it's this one. So a way of trying to give you some partial credit is by figuring out, can you at least get to this step? And then if you could do that, I think everybody in this room, well, we aren't in a room. Everybody in this class could probably take that and shove it into Wolfram Alpha and figure out how to do the integral for you. But so that's more of my concern, is making sure you know how to set it up. And there's 1 or 2 questions I think later where I actually have you do the integral. All right. So just be aware there's going to be times I ask you to do integrals, times I just ask you to set them up. And for there, that's it. All right. Now, after this is all math now. So we're done with that. Let's go to the board and see what else we've got here. Sorry, the screen share. Okay. Oops. All right. So here we go. So we did everything up to there, and then it was just math. So plug in the pieces. We did that. Here's something we could do. Determine if symmetry will cause things to cancel out. Oh, this is a tricky one. Pick the correct limits based on the coordinate system you chose. That is tricky. Let's make sure we do that. That was one step I forgot. So let me go back and do that right now. Okay. All right. In this case, think. This is a dx integral, dx. And if you don't like it sitting there, okay, that's fine. I'll move it to the end if you want. There's a dx. It's a dx integral. That means we need limits based off x. So think about it. We'd probably need to know this distance because it doesn't start at 0. Let's say it starts right here. Let's say this distance right here is, I already used a. Let's say this is b. and it goes all the way out here to this point. So the lower limit would be B, because you start having charge when x equals B. When x is less than B, there's no charge, dq goes to 0, you got nothing. Okay, as you go outwards, think to yourself, what is the upper limit? Hopefully that's what you thought. That's supposed to be a B plus L. That's sloppy. Okay, hopefully that's what you contemplated there. All right. Get this out of here so I can see. There we go. All right. This is probably a good spot to pause and make sure you have a kind of a, or give you a chance to ask any questions. You can unmute, or you could just ask whatever you want. All right. Let me just check here. Okay, thanks, Sean. All right. Okay, I'm going to go ahead and go on. All right, so at this point, you do a lot of math, maybe use an integral table, and let's see if there's anything else in that checklist. Oh, there's a question there. Okay, got it. Now let's go here. Okay, so I think we did the limits. And notice this is a small thing right here, but maybe worth noting. You should get the results. They should be the same regardless of how you choose your coordinate system. So you may have been wondering, what if I chose my coordinate system somewhere else? The final answer shouldn't be affected by your choice of coordinate system. That's an old postulate from a guy, Einstein, I guess, right? For special relativity. But we're not doing special rel today, okay? So, all right. What else here? Okay, turn the crank, spit out the answer. And then here's some things that you want to check. And we're going to do a problem here, and I'll talk about the most common mistakes. So here are the things you might want to check, everybody. So this is important. When you're checking your results, think. You want this answer to be some kind of electric field. So rather than try and check the units in the normal way, this is the way I want you to think. Does the answer have a K on top? Yes. Why? Because that matches up to KQ over R squared. That's the electric field for a point charge is KQ over R squared. That's this one. So we know the units have to match up to that. So now I need a charge on top. I've got it hidden inside here. Remember, this is coulombs per meter. So here I have K on top, and then I have coulombs per meter for this one. And then I've got times meters for this one. And then down here, I've got meters squared to the 3/2, which this is maybe looking bad. Oh, whoops. Sorry, I'm not screen checking the units right now. Okay, so I'm trying to check the units of this stuff down here. Okay, sorry about that. I've got a K on top. The lambda has units of coulombs per meter, so that's where that comes from. This whole junk right there is meters. This thing is meters squared to the 3/2, which squared to the 3/2 becomes meters cubed. It looks like something's wrong. Let's take a look. This meter cancels. I should have a K on top, coulombs on top, and meters cubed. Oh, sorry, meters squared on bottom, right? Think. Where's the other thing with units of meters? Right there. dx has units of meters as well, right? Because that's a small length. It's not, whoops. dx is this small length. It's not 0. It's like 0.005 microns, right? There's some kind of meters associated with dx. Think about it up here, right here. dq is lambda dx. You got coulombs per meter. This had to have units of meters, otherwise the problem doesn't work. So we actually have the units working out, and that's how you could check this. Is K on top? Do I end up with coulombs on top and meters squared on bottom? And here that works out because one of these cancels one of those and we get a squared. Oh, she's down here now. This one. One of these canceled one of those, and you get a square. All right. Let's see what else we got in there. Okay, so let's go back to the main screen there. So that's how to check the units on that. Direction. When you get done, you should know the electric field points away from plus and towards minus. That should give you an idea, are your I hat and J hat components got the correct sign on them? This is something you'll see matters in a couple of the problems. A common denominator can make the result of a sign more obvious. So, for example, this little term here shows up in I think one of the next problems. So rather than leave it like this, it's not obvious right away that this is actually smaller, right, than that. But you're like, oh wait, L is bigger, and then you have to do a lot of thinking. Remember, you're trying to communicate with others in a way that reduces their confusion. So yeah, is this more work for you? Obviously. But does this help somebody else that's reading it? You bet. Because now they can say, oh, this is clearly negative. And that can help you find out in combination with B, if you use a common denominator, that can help you check your minus signs. Finally, this is something you should think. As you get far away from a charge, usually the electric field should be smaller. Not true if you have an infinite plate, or but other than that, yeah, we don't have a lot of infinite plates in real life. But so yeah. Finally, I cannot stress this enough. This is probably the most common mistake I've seen in face-to-face classes on a test. Okay. This is true. Let me get my annotation here. This is good. You could do this as long as you use the full vector. Vector fields add up. You cannot add up the magnitudes. You can't just say, give me the electric field magnitude and integrate it, because sometimes the directions don't point the same way. So this is not true. Boo-hoo. It'd be nice if it did work. Okay. That is kind of the brief synopsis of how to do rods, and then we can take it from there. I'll pause for a sec and check. Any questions on that? All right. Okay, so let's take a look at the next question and see if we can do it as a team here. So let's start with the simpler one that has an easier integral. Agreed? So here we could see I redefined A as this distance. So let's see if you could set this problem up without me doing it for you and without looking at the solutions right away. Or if you're already looking at the solutions, that's fine too. Okay, but see if you could set this one up, and I'm going to set it up, but not show you my screen until the end. It'll be really tiny. So try not to look at me and do it yourself, okay? And if you get stuck, oh my gosh, just use the solutions first. So I'm just trying to catch up and draw the same figure that you're drawing. Okay. Charge Q. In case you're wondering, unless otherwise specified, just assume it's positive. Why? Because the answer still works if Q ends up being negative. So if you're not sure, just assume a charge is positive, and then at the end of the problem, you can always set Q to a negative number, and that will flip all your signs, and you'll still get the answer right. If in doubt, assume Q is positive. Okay, so we got this thing in here. So now I'm going to say, okay, I want to get the electric field. So I'm going to do E is equal to the integral of dE vector. I can't do E equals integral of dE magnitude. I have to use the vector. In this case, it's going to be K dq R vector all over R cubed. And again, you could use R hat and R squared. In this case, what's this R vector, right? In this case, it's from the source to the POI. So it's not X, it's negative X I hat, right? It's from the source to the point of interest. Now, R is actually pretty easy. That's the magnitude of this, right? So that would just be X. So here, because X is positive, we don't have to worry about any of those weird signs things, okay? All right. Next up, we can now plug, oh, and then I guess I should say here, I expect this is a uniform rod. I want to check that. Somewhere in the wording, it says uniformly charged rod. I'll show you. Uniformly. If it's uniformly charged, that's when we know this. Total charge over total length. So if it's uniformly charged, this is a known, okay? If it's non-uniformly charged, I'll explain that in another problem. Next, dq. I need dq. In this case, dq is just going to be lambda dx. Okay, lambda dx. Let's see, do we have all the pieces? I know dq, I know r, I know k is a constant, so we're ready to go. So next up, we fire this up.
I have a quick question.
Yeah, go for it.
Why is, oh, never mind, I figured it out. Is r hat, or the r vector is negative because it's going from source to point. Thank you.
From source to POI, yep. And so I think in this problem, just to be clear, I guess I didn't say that. Let's make sure we see that in the question. It says choose point A as the origin, and I'm supposed to get the electric field at point A, okay? So because the problem said I want the electric field at point A, that's what told me I want this. It's not because you always use the origin. It's just because this problem asked you to use this, point A, as the origin. Yep. Good stuff. Okay. All right, so we're forced to choose this because that's what the problem told us to do. Next, I just keep rocking here. K, I'll get that, lambda dx. That's dq. R vector is negative x in the I hat. And then over here, r cubed. Well, that's just going to be x cubed. And I see that right away, I can cancel out one of these x's. If I make this a squared, notice that's r hat over r squared. Right? Isn't negative I hat the same thing as r hat? R vector divided by r gives you negative I hat. So this is r hat over r squared, same thing. But let's get the limits right. In this case, no charge, no charge. I start when x equals a, when x is distance a, I get some charge starting. So it's going to start at x equals a, and then I go L past that. Well, if this is A and that's L, this whole thing is L plus A. Gee, I wonder which problem is going to use the common denominator trick. Okay. Let me check here. That's right. No, Sean. Oh, let me see what. Let me read Sean's question carefully here. Yeah. So again, Sean, you are right. But if we were calculating electric fields, we would not want to do it that way. We always want to go from source to POI. And so it's you. I believe you're correct, but it wouldn't be useful. Yeah. Or well, yeah, it wouldn't be as useful. All right. So now you're up to there. This is just math. Let's take a look here. So let me get the solutions up really quick. And I'll let you keep grinding there. All right. And so what was this? 22.10. Oops. Okay. So here's all that stuff. We kind of just did all this junk. I guess I jumped ahead to right here. We plugged all that in. I think this is where we got to right there in our work. So we're kind of looking at this stuff down in here. So you can see that in the workbook, I really tried to walk you through this in baby steps. So I'm looking at this step. That's where we stopped on the whiteboard, okay? And at this point, this is a constant, this is a constant, and negative I hat is also a constant. That's why those pop out. This is a straightforward integral. You get this result. I'm going to pause for just a second and see if there's any questions on that. Okay. And when you grind that out, it's just boring math. You get this cool result. All right. I'll give you a second to kind of follow through here, because I want to actually do one of these with the checks, because I think you can learn a lot when you do the checks. Okay, and so I have no idea if I'm going too fast, but I'm going to get back in here. All right. So all I did from here, that was just copying there, and I think a minus sign cancels, which maybe this makes you worried. If I go back to my board here, look at this thing. If this is a positive charge, shouldn't we expect the electric field to point negative I hat, which we did have here for a while, but then the minus signs canceled. Just trust me, work out the math all the way before you check your signs, okay? And that's what we're going to do here. So here I plug all that crap in, and notice right here, this term L plus A has a bigger denominator. So I can tell it's a small number minus a slightly larger number. It's going to give me negative I hat. It's going to work. So here's just doing the common denominator. Here's doing the common denominator. And notice when you do the common denominator, I think it's slightly easier to see that this is negative I hat. Finally, it's very common to take lambda and replace it with lambda equals Q over L. if it's uniform. If it's non-uniform, you can't do that, okay? If it's non-uniform, lambda won't be in the answer. But when I do that, look at this crazy looking formula here. Okay, I'm going to scroll down to it. And look at all these things that I checked on this. So the idea is, you know how hard this class is. You know how hard physics is. The more ways you have to check your work, the better it is. And this is a good habit in any branch of engineering, right? The more ways you could check your work, you see me, I'm making mistakes all the time. Everyone makes mistakes. But the more ways you have to check your mistakes, the fewer you make and show to your boss. If you're showing mistakes to your boss all the time, they start to be like, let's fire this guy. Okay. Unless you teach at Hancock, and then you can somehow survive no matter how crappy a teacher you are, right? Like me. Okay. Yeah. Oh, Zoom humor. Okay, so let's get to this. Does it point in the right direction? Yes. Let me get the annotator because I hate this thing here. There we go. Okay, does it point the right direction? You bet. Do the units check out? Take a look. I've got a K on top, a coulombs on top, meters times meters. Yes. And remember, I hat does not have units. Hat vectors never have units. That's what's different about them. Hat vectors have no units. Kind of a misnomer, right? Unit vector have no units. Okay, so the units check. K on top, so got that. And meter squared on bottom. Whenever possible, try to consider large distance limits. So this is a little extra. This is a little icing on the cake, but I think you'll like this. Think about this. What if A is really big compared to L? If that's the case, I hope you agree L shouldn't matter that much. If A was 1 billion and L was 1, 1 billion versus 1 billion plus 1, who cares? That's negative KQ over A squared in the I hat. Now, that makes sense to me, okay? Think about this, and I'll try and show you here, okay? Imagine we've got this rod here, right? If you're this close to it, clearly the part that's closer to me is going to have a much bigger effect than over there. But if instead, let's say I go way over here where my fist is. This is so far away from that rod way over there. You could think of this rod as being a point mass or a point charge. So if I'm really far away from that, way over
We can't hear you.
I think you might have yanked the cable. Oh.
Yeah, I yanked the cable. Sorry.
So it's kind of like the parallel axis theorem with torques.
Yes. Yeah. If you go far enough away, you could treat it as a point mass. Absolutely. Is my audio back live? Okay, thanks.
Yes.
All right. I appreciate it. And let's see if there's something else to say about that. Okay. Oh, here's the other limit, right? If you go to 0, think about this. If A goes to 0, you're really close to the rod. You're going to have nearly infinite field because you're so close to it. And you can see that one way up here, right? If A goes to 0, this thing blows up to infinity, negative. That makes sense. If you're really close to a charge, the electric field gets enormous. All right. What do you think? I'll just check. Making any sense?
Yeah, making sense.
Okay.
I have a question. It might be a dumb one.
No, go for it.
When I did my integration to get -1/x, and that canceled with the negative I hat, and I got a net positive answer, but the solution is negative. Am I missing something?
Yeah. Remember, when you plug in the limits, you should get negative again. So let me show you again.
Okay,
Sorry.
thank you.
That's the most common mistake, yeah, on this one. Take a look. You get positive right here, right?
Yeah, I do.
And then when you plug in the limits, this term has a bigger denominator. It's a smaller number. When you do the common denominator, you still get the negative popping out. So it does work. And that's what I was saying is if you don't do the common denominator, sometimes it looks like you're wrong when you're not.
Oh, I see. Okay, thank you.
All right. Yep. All right. Other questions? Yeah, go for it,
I
Ryan.
just did, so when I pulled out my constants, the k, lambda, and the I hat, I pulled out the negative with the I hat.
Right.
And then I did my limits and stuff with the fractions and common denominators all separate. Is that ever a bad way to do it? Is that particularly?
I don't know. I can't think of a situation where it would really matter that much.
Okay.
Yeah. Yeah.
Okay.
And as you'll see, how would you do this in the real world? Anybody?
Plug it into an integral calculator.
Okay, yeah, that's true. Or just code it in Python, which is what you're going to do next week in lab, right? So whenever you get these things, rather than do continuous distributions, the real world, you're always doing numerical approximations and coding. So the idea is we're going to do a numerical sum, and we'll basically be doing numerical integrations in Python to do these kinds of problems. And then you don't have to know Alexis's trig sub, wherever Alexis is, somewhere in there. It's pretty weird with 50 people here. But yeah, so you don't need to know all the integral tricks if you just do sums. And it's like, oh, and that's more powerful because not every problem can be integrated analytically. If you start plugging stuff into Wolfram Alpha, it gets insane really fast. And I know this sounds crazy. I think you might even be able to use your computer codes to help you during your quiz next week or the week after if you write them correctly. And I'm not offended by that as long as you're using your own code. Yeah, right. Because I'm going to ask you to do problems and screw it. This is online. Anything goes as far as if you've got something that we can use. There's another problem. I literally tell you, use Wolfram Alpha for this calculation. So there's going to be some different time. You got to free your mind, man. And yeah, get into that. So whatever possible, get that coding experience. That matters more than the physics. All right. Other questions? Sorry, I'm babbling today.
No, I did the expansion too and got my negative again. Thank you.
Right on. Cool. All right. Now, this might be a good time to take a break. It's almost 5:55. If you don't want to take a break, you could just go on and see. Here's some of the other ones. And notice in this case, I gave you some different coordinate systems. So the idea is you could do these problems right now and see, okay, what would be different if I use this coordinate system? You know the answer. Well, I'll talk. Yeah. So I'll take a break right now, and then we'll come back and take a look at some of these. Okay. All right. Yeah. Oh, geez, I'm not screen sharing. Jeez. I'll show you again. Sorry. So sorry about that. I was just looking at the problems on the next page, 22.11 and 22.12. If you want to work on something, you could start working on those. You could see here we get a non-uniform, and this will just beat the crap out of these. So yeah. All right. Now I'm going to take a quick drink break and restroom break. Oh boy, back for more. All right. Hopefully this is about right to get started. I'll give you guys just a second. All right. I think we were working on page 20. All right. So, oops, let me share. All right. So we kind of looked at a number of these things here. We saw that there's a lot of different rod problems. And you can see I tried to give you a bunch of different variations on this. All right. And so we just did that one. That's right. Okay. So now I'm going to let you try 21 or 22.11 and 22.12. I'll also let you try 22.13. Those are all uniform ones. And so you've got the solutions, and you can see that there's a lot of these concept questions snuck in there. I love those. All right. And so what I'd like to do now is try a non-uniform rod and see what, if anything, is different. And it's also very similar to some of these other ones. So hopefully you can get practice trying those other ones. All right. Oh, insane challenge. Yeah. All right. So this is a good spot to be. 22.14. All right. So that's what I'm going to start writing up on the board. If you want to start working on it, you can start working on it as well. Make that just a little bigger. Oh, that's a lot bigger. I guess I can't fit it all.
I have a random, hopefully quick question you
Sure,
can
go
elaborate
for it.
on, hopefully.
Yeah.
Why is dq in our equation? Why did you know that was lambda?
dq is not lambda.
Oh,
So dq
What was
is
that?
lambda dx.
right. Okay.
And so basically I was checking the units. This is a good question. Good question. That's the kind of thing we should be talking about right now. Just give me a sec.
Okay.
All right. So in this case, we're talking about this new thing, charge density, right? So charge density is right here. Lambda is charge per unit length. So, right, we're just saying take the total amount of charge, and you could think of it, how do I get the charge on this tiny little segment? Isn't that basically taking a ratio? You take the total charge and then say multiply by this length over the total length. Well, that's what this is. Take the total charge per unit length and then multiply by the little segment that you do have. You're basically taking a ratio to get the amount of charge just on this little section. Is that good?
Yeah. That
Right
makes
on.
sense.
Right on. Yeah. Okay. Good. All right. And then going back to this one. There we go. So I'm going to start drawing this up on the whiteboard, starting here. Okay. Okay. So in this case, and then we're told lambda alpha x squared. Total charge Q. I think I got everything now. Okay. All right. So we have this rod here. There's some charge on it. And this time, maybe what happened, let's take a look at this density and get a feeling for it before we get too crazy, okay? In this case, we see that alpha x squared here, right? Think about it. It doesn't matter whether x is positive or negative. When you square it, you're going to get a positive charge density. So we know everything on this rod is positive. Furthermore, we know if x is a big number, there's more positive charge. So just imagine I rub this with fur a lot, a little bit, almost none, not at all. A little bit more, a lot, and a ton. So again, we see that there's going to be lots of plus charges here and here, none in the middle, and a few in here. Okay, so that's just giving me an idea for this. Based off that, think, which direction should the electric field point? At P, what direction is the electric field going to point?
Straight up.
Probably straight up. That's what we would expect, because there's the same amount this way and that way, and we'd expect no matter where you are, you get some symmetry there. And I'll do more on symmetry at the end of class when everybody's beat, okay, in like 10 minutes, 20 minutes. Okay. Now, pick a random chunk. Here's a tip. If you're not sure, pick a random chunk in the first quadrant, okay? So just pick a random chunk, call that dq. Now, dq is not dx, it's not lambda, it's lambda dx. It's the product. And now here is my r vector from the source to the point of interest. From the source to the point of interest. I write down the electric field you're going to see I get pretty lazy and skip right to lambda dx. This is k dq. And then I got to go over r squared. And the r, actually, I'm going to do r cubed and r vector just because that's easier for me. So now what I need to do is figure out r vector and r magnitude in terms of these symbols. All right. Now I'm running out of room here. Let me move this way out of the way here. dq is lambda dx. This whole chunk right here is that whole chunk right there. So now I look at this and I'm like, well, I know this distance is defined as the symbol y. Well, I don't know what this distance is. I need a good name for it. How about x? Right? Why did I call this dx? Because it's a small distance in the x direction, right? That's why this distance right in here is dx. It's a small increment in the x direction. So this is a small amount of x. That's why it's dx. We're x over. All right, this is looking pretty good. So I think this is going to be negative xi hat plus yj hat. Okay. This down here, well, I could see it's going to be x squared plus y squared to the 1/2, which will give me there we go. I'm going to check my limits. I'm going to check my limits. In this problem, whoops, where are we? Right here. The total rod length is L. Look at that first line of that. Total rod length is L, right? Well, so what are my limits? It's not negative L to L. It's not 0 to L. Hopefully you got it. I heard somebody unmute. My bad for cutting you off. Hopefully you saw that the limits are negative L over 2 to positive L over 2 in this case. Okay. So that's pretty good. And this integral is ready to go. think, how could we save ourselves some work here? And this time I will wait for somebody to respond. My apologies. So somebody go ahead and tell me, how can we save some work here? How can we make this integral easier? In this special case, for this particular problem.
Can you break it up into two portions since you have your y?
You
and you're doing
could.
the j hat direction?
You could do even better. Which one drops out?
The x completely drops out due to symmetry.
Exactly. Yeah. Remember at the very beginning, I kind of snuck that in there. Don't we expect the final answer to point straight up? If that's the case, we don't even need to do this one. I'm just going to cheat, right? So it's not that that isn't part of the total equation. The issue is that, like Jay said, if I split these up and do two separate integrals, we know the answer to the I hat integral will be 0. So I'm not going to waste my time doing it. And that's where the conceptual side of this class can save you time on a test or something. Okay. So is everybody, I'm just going to write ignore by symmetry here. Okay. So you're going to hear physicists say this all the time. By symmetry. Blah, 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 blah. Gregory. Yeah.
I'm confused.
Go for it.
If this is non-uniform charge density, wouldn't it not be uniformly pushing straight up on that, and the x wouldn't cancel out then?
That's an interesting thought. And remember, if you weren't sure, you could just do the integral and discover that it is 0. So if you weren't sure, you could do it and you'd be like, oh crap. And then you'd be like, now let me show you this though. I'd like to come up into here. Remember, we're told this thing is centered. So we know that. If I go over here 3 meters and I go over here 3 meters, I'm going to get the same amount of pluses. 1, 2, 3, 1, 2, 3. Now, if I go over, there's none in the middle. And then right here, maybe there's 2 or something. Right here, maybe there's 2. So the idea is there's not the same amount of charge at any point on the rod, but we do know this point and this point have the same amount of charge. They're equidistant. And if I could,
I totally get it. Yep.
That's that way. This is that way. And so for these two parts, only the j hat survives. And that's going to be true. Every single spot on this side has a corresponding shadow spot on this side. And that will, good. Yeah. All right. And let's see. At this point, before we go on, let's be careful here. Let's pull out the constants here. Think to yourself, and let's see. Is it not in the PDF? If it's not in the PDF, I'll get you there. Oh, okay. Sorry. All right. Let's think. Let's pull out all the constants. So I'm going to do some work on the board, and I'm going to do it incorrectly on purpose. So I want you to figure out what I did wrong here. I know that. This is not right. What did I do wrong?
Lambda is actually alpha x, so it's not a constant.
Yep. Because lambda is alpha x squared for this problem. If this is the main difference. If you have a uniform problem, lambda is a constant and pops right out. If it's a non-uniform, we have to plug in what that is. Lambda is actually alpha x squared dx. And now you might be saying, oh, how am I going to check my units on this? It's almost impossible to check your units with these problems unless in the first step of the problem, like part A suggests, get the units of alpha so that you can actually check it. So in general, when you see these types of problems with a non-uniform density, the first question on a test is usually figure out the units of that constant. That way you could check your units at the end. Now, how do I get the units of that constant? Up here. I know that this is coulombs per meter. This is the units of alpha, and this is meter squared. So the units of alpha must equal coulombs per meter cubed in this case. So if I needed to check my units, I know this has got the coulombs, And it's going to cancel out these 3 meters and blah, 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 blah. Oh, I've got a meters here. That could, okay, the units check out. Let me pause here. Okay, yep. Yeah. So we're looking at 22.14. Sorry about that. I forgot to mark that on the board. All right. Let's see if I want to look at the solutions really quick, see if there's something I forgot. And let's catch up here. Let's read the question again, see if we're going the right track. Okay, so determine the units of alpha. Which sections of the rod carry the most charge? Determine the constant. Oh, we didn't do part C. This is an important one to do. Okay, so we'll do that in just a second. Part D, I think we figured out the direction. We discussed that. We said it's got to be straight up by symmetry. And notice we do that before we actually figure this out. All right, and notice here I said this is one of those problems where you'd use an integral program. All right, so now I want to go back and make sure we do this part. I think we accidentally skipped over that. Okay. All right, so one last bit here. Okay, in this case, it says there was a question part C. So this was 22.14C. Relate Q to alpha, I think, right? And L. Something like that. Alpha, Q, and L are all related. Figure out the relationship between those 3 variables. Well, think. I don't know much more than this. I know that Q is equal to all of the charge. Well, what's a fancy way to do that? Isn't that the same thing as adding up all the little charges? Well, isn't that the same thing as just saying Q is equal to the integral of dq, which is equal to the integral of lambda dx? And that's actually a quick one. This is useful for reasons we'll see in just a minute. Okay, the idea is I could plug in that this is alpha x squared. This, oh, well, I got that. And then my limits are, geez, negative L over 2 to positive L over 2. I could do that integral, piece of cake. You could probably say, oh, well, isn't this a symmetric function? And yes, even limits, and absolutely you could do that. You could go from 0 to positive L over 2 and double it. As we discussed earlier, like when Ryan was asking, said, oh, well, we got the same amount of plus on each side. You could just go from 0 to L, 0 to L over 2, then double it. Okay. All right. So now, why would you do that? I want to show you in the solutions why. Okay, so oh, come on. Why is it not? Okay, I don't know what's going on there. All right. So this is my attempt to kind of show you what's going on with this rod. A little bit slower, right? So, okay, this looks good. So the color, I tried to give you an idea of how much charge is there with that. This is that integral that we just talked about doing. It's not too hard, blah, 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 blah. There's the limit crap. So notice, this is the advantage of doing this. At some point later in the problem, alpha is going to be sitting there. I could care less about alpha because that doesn't have a lot of physical meaning to me. But what I can do is I can rewrite alpha in terms of things that do matter. The total charge on the rod and the total length of the rod. And those things have more physical meaning to other human beings as well. And so by doing this, this allows you to get rid of alpha in your final answer. That's all we're doing that for. It's to help other people understand what the heck you're talking about. All right. So this is kind of going through this one. Oh, that's funny. Yeah. All right. So I should say that should be a DE, not a DF. My bad. All right, whatever. So then, okay, oof. All right. So this is where we got to, and this is now just like ridiculous, right? So this is the point where you just go to an online integral and do it. And oh my gosh, look at that crazy. Ugh. So we are not going to do that on quiz 2. Yeah. Did you do it by hand, Alexis? Oh, man. Ouch. Oh, Matic. All right. Well, cool. Yeah. I like the trig subs too, but even I kind of got crazy there. You'll see, I don't know if you noticed this. Alexis mentioned trig sub twice today. If you're curious why we're doing so many trig subs, the reason is we got lots of triangles on the board. When we're doing these integrals, right, we're getting stuff that looks like, whatever. You see lots of triangles in these problems, and that's where the trig subs come from. Anytime you're integrating like this and you see a triangle, that's a hint. Oh, trig sub, triangle. Anyways, all right, good enough on that. Yeah. Oh, this is a challenging one. Oh my gosh, this is crazy. Yeah. So if you really want, do not do this unless you're really, something's wrong with you or you're like really wanting to have fun, whichever one. Yeah. Oh my gosh, that's crazy. So let's go back to here. What was the question? Whoops. So in this one here, this insane challenge, this is what I was curious about. I thought, if I'm going to do this stupid problem, I want to make sure that when y is much, much bigger than L, so when I'm really far above the rod, shouldn't it be a point charge? And when I saw that sick equation, I'm like, there's no way this is, I must have made a typo. And then I punched it all in, and sure enough, it actually worked out. So I had to do this crazy series expansion. Gosh, it was really nutty, but yeah, it actually works out. So that's cool. Mathematics is fun, or whatever it is. All right. That's the rod. Okay.
George, Dad,
Yes. Question.
can you quickly explain the limits again?
Yeah. So for this one, I think this will help. Let me go back up here. Right here, and let me make this bigger. Okay, in the problem, they told us that this entire distance, we said the rod had length L. And because I'm assuming it's centered on there, this part should be L over 2. And this distance over here should also be L over 2. But then I have to be careful. If I move this way, it's positive L over 2 at that end. If I go that way, I'm getting a negative L over 2 because I'm to the left. Hector, did that address your question?
Got it.
Right
Thank
on.
you.
Yeah, for sure. Other questions? Anybody? Anything?
Yeah. So, like you were explaining to me earlier, there's kind of equal amounts of charge on either side of the rod of what we were looking at. Our coordinate system went right through the middle. Say we were given a problem that had a rod with lots of charge density on the left side and very little on the right side. Mathematically, all that would change really would then be like the equation for lambda that we're given.
Yes.
And the integral. Okay.
Yes. Yeah.
Okay.
What if it was lambda x? Ryan, I'll put you on the spot.
Yeah, you're putting me on the spot.
Good. All right. So, whoops.
Wouldn't that just be
my computer's
uniform?
locking up. My computer's locking up. Can you hear me?
Yeah.
Okay, hold on. Something's messed up here. Hold on. Oh, there we go. All right. Let me get back to this one. The reason I asked this is because it's the next problem in the book. Okay. So I wouldn't expect you to know this right off, but I want you to think about this. Okay. So now think about how the density changes. I want you to get a feeling for thinking about the function, the density function, and what it means. So alpha x, if you're on the positive side, what's going to happen, Ryan? Is it positive or negative?
Sorry, say again.
Oh, if x is a positive number, what happens to lambda? Positive or negative?
Oh, positive,
And if x is a negative number,
negative.
right on. So then, do you agree it would look very different from this?
It would, yeah.
Let's go look at it. Whoops. I can't see where I'm at. Oh, that's too far. It would look like that. You see that?
Oh, interesting. Yeah, yeah.
Now look at this sucker. And I don't know why I called these Fs, but yeah, you could imagine if you put a little positive charge here, the DF and the DE are interchangeable. I need to fix that up. But now think about that. Notice in this case, by symmetry, which component survives?
The X.
Yeah, so in this integral, you'd throw out the J hat part and only keep the I hat. Whoa, smoke that crack pipe. It'll really get you out there. All right. Let's call that good on that one. What do you think? It's kind of fun. I know that seems crazy, but this is where it starts to get fun. Well, I think it's fun. Yeah. All right. Yeah, and those of you that had 162, you probably have a little bit of an advantage here because you know about density functions and quantum mechanics, right? Maybe. And so the math that applies to these ones is very similar to that. And then in that, and those of you that just had me for 161, you actually have, you're very used to my style for point charges and things. So you got an advantage on that one. So yeah. All right. Some weird things that happen. Oh, let's call that good on rods. And I think we have 10 more minutes. So I just want to foreshadow something, then end with kind of a fun, easy mathless question. Okay. Yes. Okay. Yeah, totally. Let's see. Let me go to here. Oops. There we go. So let's scroll down. That was rods. You could do rods till you're blue in the face. Okay, got it. Now, what if you have a ring or an arc type shape? I'll be straight with you. The most common types of questions that I might put using calculus on a test, either in this one or the 2 chapters from now, they both have this similar type of stuff. It's usually a rod or a ring or an arc, okay? So you definitely want to know page 22 really well and the problems associated with it, as well as 19. So 19 and 22, those are probably the most important calculus ones to really make sure you know. Now, this is a little bit different. What we're going to try and do is build up a ring out of here. And the idea here, I'll go through this very briefly, and we'll probably pick up here next time. You could split this into little chunks, and then you got an R vector that comes to here. And notice you're going to have an R vector that's now 3-dimensional. And so we kind of have to deal with the 3D factor. It would be, say, negative X in the I hat, negative Y in the J hat, and then some Z in the K hat. And maybe you see why I was torturing you with the 3 balls on a string. So I'm trying to get you to help deal with the 3-dimensional vectors because that's just an essential part of this course, whether we like it or not. So if you hated those balloon problems, hopefully this will be a little bit easier because you did it. And that was the goal. I don't know. We'll see. But so, all right, let's go up here and take a look at this thing. The idea now is, again, we're just going to build up that thing out of point charges. And there's a couple of little tricks here that are slightly different. We still do pick an arbitrary chunk. We still write down the R vector. We still get these craps. And then we still do the same thing with the density. You got to be careful, though. Look at it. Let's go. Whoops. Let me scroll down here to this particular problem. In this particular problem, what's the distance all the way around? 2 pi r, right? And so in this case, lambda is going to be, if it's uniform, it's the total charge, which is Q, over the total length, which is 2 pi r. And so notice it's not Q over L, it's Q over 2 pi r. What if it's only half of a circle? Then it'd be Q over pi r. What if it's only a quarter arc? It'd be Q over pi over 2 times r, which is 2Q over pi r. So this is where it gets a little bit tricky. With an arc, you have to figure out how long the arc is using S equals R theta. Oops, R theta. Okay, so if you want to know the distance around, it's R times the angle in radians. And so we'll be using that a little bit. Let's go back up there and see what else we've got. And so notice, instead of doing lambda dx, it's going to be lambda ds. Well, an arc length, that's the same thing as r d theta. And from there, you could kind of do that. And we're going to pick this one up next time. So there's not enough time to really do this justice in 5 minutes. So I'm going to pick that up next time. But I'll give you a hint where that's going. You can see, and then this one, I think this is good for you to do. But to be honest, yeah, probably this semester, I'll just tell you to do that and make sure you do it for the homework, but you don't have to stress when studying for the quiz, okay? So I'm not going to do this particular question on the quiz or that one. All right, and there's a whole bunch of arc questions if you need practice. Now, to finish, let's go back and do one I skipped over early. These ones, these are kind of fun to end with. Okay. So there is definitely a question like this on your next quiz where I made some charges and I put them out there and I said, okay, try to figure out which ones don't matter or which way the net charge is, or what the net electric field. So I'm tired. Okay, let's go through this. Look at the following charges. Figure out the direction of the electric field at the center of each one. And so this is what you're supposed to do. Right at the center. Let's take a second. Now, why are we doing this? This helps you understand symmetry, which could make later problems easier, okay? Also, it's just slightly fun. So think to yourself, if I'm sitting right here at the middle, what direction is the net force? And try and do all of these really quick, okay? What way is the net electric field? I think I said force, excuse me. And I'll try and maybe do one of these. So these top two positive charges would push it away. These bottom two are negative charges, so they're going to pull it towards. Hopefully you could see that the lefts cancel out and the net effect is straight down this way. Okay. And the idea is you could do a couple of these and you could also use the FET, and I'll get that ready. So let me do that. I'm going to go ahead and do this for a sec. Hopefully you've got these problems in front of you, 22.5. Let me see, there's a question in the chat. Oh, gotcha. Okay. Hopefully that's a little bit of a fun way to end class after a torturous day. What is going on here? Keyboard's not working. Oh, whoops. There we go. So just to end with some fun with these ones, you could put these out on the grid. Right, and the idea is if you put a plus charge here, pushes away, a plus charge here, put a minus charge there, and a minus charge there. Notice that right at the center, we see the electric field is straight down. Now what happens if you switch these? The the idea is hopefully you get a feeling for that. Where was that one? Notice you can kind of think through these. And so you could imagine I took 20 different pictures, stuck them all on there. And so you guys are each going to have a different set of charges. And the trick here, there's another one. I do want to show you this last trick on the way out. We got 1 minute. Let me get back to it here. This is a cool trick you should know for the quiz. Look right here. This charge and this charge are exactly opposite. Ignore them, right? They're going to push and pull, or I guess in this case, they're pulling opposite ways. So one of the first things you want to do is look around and see if there are any pairs that cancel out completely. And in this case, this one and this one, they're going to push and they're also going to cancel out. So this one, there's no field at the center. Now over here in this one, let's look if there's any cancellations. This is a plus Q, this is a minus Q. Well, that I do know that that's going to end up being a net effect this way, right? Because the Q pushes and the negative pulls. So you could start by looking at these in pairs, and sometimes that helps. Now I've got a plus here and a negative there, and it's twice as big. So that's going to go this way. And so now I could see by the parallelogram rule, it's probably right out about there. And so maybe these kinds of tricks can help you see. I'm promising you that it's on the next quiz. So that I'm hoping this will be the easy one. All right, let's not talk about the quiz. That brings up bad memories. All right. So, hey, I know you guys tried hard on the quiz. I will look at it and I'll just keep working at it. I feel like I'm a brand new teacher. It's very frustrating because I know a lot about what I need to say to help you learn something. But all the technology and everything is just so hard to deal with on your end and my end. So you just have to trust me that I'm learning about your ability to respond to my questions at the same time that you are. And I'm willing to take that into account at the end. Don't think I'm going to be like super nice or anything, but I'll probably be a little bit nice, right? You don't want to count on me being nice. And hopefully I'll pleasantly surprise you with some niceties at the end, but I'm not going to tell you I'm going to be nice. All right. Yeah. All right. Okay. So let's call that good. I'm going to end the live stream, but I'm going to stick around for the next hour. Anybody that wants to talk about questions, I know Alexis is chomping at the bit to get some question answered. He's been emailing me. So, yeah, let me stop the live stream before I forget.